Hey everyone, so in this video we are going to be looking at data from Bigmart sales data, and we'll be working on predicting the sales of product at each store level. Now before we jump in, I'll give you a preview of what we can expect from this video. So we'll do some basic exploratory data analysis like this and a lot more as well. And we'll run some SQL queries to understand the data a bit better. We'll also run through some analysis to understand the correlation, causality, and collinearity between variables. And we'll approximately run through 8 to 10 different algorithms within this data set that we've been given to get to a regression solution. So if I come into the Kaggle actual website, so I'll share the link within the notebook as well. And this is the data that we've been given, and our aim is to build a predictive model to find out the sales of each product at a particular store, which is Bigmart in this case. And you can come in and read through the data as well and what kind of data we have. But if I scroll to the bottom, you'll see there are two files. There is a training file and a testing file. And you can see all the columns within this training file and the testing file. And the column that we're interested in is actually hidden over here in the item outlet sales. I'll also bring in these two columns. So if I click on apply and scroll to the right, so this is the item outlet sales, which are all the values that we are trying to predict when a new value is given to us. So with that being said, you can go in and explore this data set a bit more and download it and call it train.csv or any file that you would like to call in your local machine, and then start running from there. So you'll also notice that I'll be running this as an interactive mode, not in a Jupyter notebook. I just find it personally useful to be able to run it like this because I can literally click on any of these lines to just get a value from there, which you'll see in a minute. But you can run this in many of the popular IDEs like VS Code or JetBrains packages or whichever tool that you're using. So let me just bring in these two packages right now, and if I run this, you should see that these two packages are in. I as we go along, I tend to put in a lot of notes here just to give you a bit of context when you do get access to this file. Try to read through that and also try to do a bit more research on your own so that you can understand all these concepts a lot better. But as you'll see in this video and in also the future lab sessions that I'll be sharing notebooks for, it kind of follows the same pattern and again, where we do the exploratory data analysis, the analysis, and evaluation. And if you hold on to these notebooks and if you're able to replicate some of the functions that we write in this in the future lab sessions as well, now that gives you a really good foundation so that you can use that in any problem that you encounter, not only on Kaggle, but in your real world businesses as well. So I kind of encourage you to build a repository of all these functions, calculations, and knowledge base so that when you do get to use this in real world, you have some foundation that you can build off of. But let's also bring in the training data. So now we have the training data over here. So now if I click on view as data frame, we can see all the data that we have that were downloaded from that CSV, and also finally the item sales as well. Now within this data set, it's quite fortunate that we have a data set which is sort of clean, but you'll notice it's not that clean. We still have to work on it a bit, but then this is in a good format where we can start working with this. Usually that's not the case in real world. You have to go into the database, or you have to work with a data engineer or data analyst to get this access to this data. And most often you will find them using tools like this where you have to write a SQL query to extract this data out. So I thought it'd be kind of interesting to also use the SQLDF, which is coming from Pandas SQL library. You can use that to kind of explore the data within SQL as well, and you can get a better intuition of how SQL works, because Python and SQL and even R, they're kind of the universal tools when it comes to building data science model. So I've just written a few SQL statements here. The easiest way to do this would be to do select from df train, which is the data frame that we've created over here. There's no other special functions that you need to initialize or convert this to be enabled to write SQL on top of it. So if you had called this just df, then you would just say select star from df, right? So if I just run this now, you'll see that I'm only selecting the distinct item identifiers from my df train, and that's that. And here are the item types, which are all the items that we have. We have about 16. And if you want to do some data cleaning as well, which we'll see further down in the video, like if I wanted to have a consistent value for item weight or outlet size, I can run something like this and finally save that into another data frame, which I can use for training and testing as well. So if I just select all of this and run, you'll see that there is a new data frame that was created. And if I do view as data frame, it'll all still be the same except for some of the values like the outlet size and the outlet type, or the other fields that we worked on, the outlet size and item weight. Right, so we are just filling all the null values with item max, item weight, and so on. So those kind of things are very, very useful when you have access to both SQL and the pandas data frame. Now we don't have to run through all of this. These I've just given here for the sake of practice, so you can see how all this works. Now let's move on. We can also look at the data types in this data frame that we have here. So we see we have item weight, which is float 64. There is fat content, which is a categorical column. So if I come into here, there should be a fat content column, which is low, regular, and other values as well. So we have both a mix of categorical and numerical values. So that's good to know. So when we're just starting out with this project, our aim is to do a lot of exploratory data analysis to actually check if the data is in a state that can be used for building data science or machine learning models on top of it. So I'll just bring in all these packages which are really useful when it comes to building plots or doing exploratory analysis. So Plotly is especially really good package. Seaborn and Matplotlib are kind of the traditional ones where you can do a lot of plotting and understand the kind of data that you're working with. So the first thing is to look at the histogram. Now, to go along with these videos, I'll also be creating a Miro board with all the information on all this and the related formulas and other things as well, especially when it comes to chi-squared and some of the ANOVA test and other things that we'll be looking at later on in this video. But before I do all of that, I just want to make sure that we do have some workable data and code in here. And that's why I've just put all these notes in here. So I do recommend you go through these notes and also do your own research on what we are doing here. So the first one is looking at the histogram, and a histogram is just a type of bar chart, and it represents the distribution of numerical data by dividing that into specific intervals. Or if it is categorical data, you can just look at the counts of categories or count of values that you have within your data set. And it really gives an understanding of what kind of data we are really working with. And let me show you what I mean over here. So I'm creating a subplot over here. So this function is actually coming from plotly.subplots, and we can create this. And here I'm giving the df train.shape. So if I just run this section, you will see we have about 12 columns. So we are just making a plot for like 12 rows or 12 columns. Actually, it is 12 rows. And we are just going to loop over all of these columns. So if I just look at what columns we are running this over. So we are running this over all these different types of columns that we have. And then we look at the histogram for each of these columns to see how the data is distributed. Now, you might have gotten a sneak preview of how this looks like. So within at least my IDE, it shows up at the top bar over here where I'm able to see some distribution. So these are all the histograms. And if you also noticed within the Kaggle website as well, at the top over here, you kind of get a distribution of how all this data is looking like. And within our exploratory analysis right now, we are going to be doing this a bit more explicitly to try to understand how all this data looks like. So we are going to loop over all these. So initially we'll get just the item identifier in this index and the column. And next we'll move on to item weight and item fat content and so on. And within the function itself, so we've initialized this figure, and to that we are just going to add a trace or a row. And to that we are going to use this function called go, which is graph objects from plotly. And within that graph objects, we have this function called histogram. And you can come in here, look through the documentation, try to understand how all this is working. But essentially, you would need to give it an x value. In this case, we are just looking at the df train and then the column that is coming from this loop over here. And then we'll just build this histogram and then add it to trace. And then we are just updating the y-axis and the x-axis with the title and maybe what kind of is it a count, is it sum, or whatever title that we want to give it to the y-axis over here. And finally, we'll update the layout as well because there are about 12 different columns. I'm just setting this at 3000. And if you're running this within IPython Jupyter Notebook or somewhere, you should be able to get this output within the cell itself. But because I'm running this interactively, I'll have to save this into a different file, which actually works in my favor because now I have some repository which I can go back to and look at all this without actually going through and running the code myself. But anyways, let me just run this section and show you what we get. So once it runs this, now we should have a file called figurehistogram.html saved. And we'll come to this section where you're able to run the similar analysis using another package called SNS. Now, you don't have to use both of them in your projects. I'm just including here so that you have really different options for trying out this data exploratory analysis, whichever way it is easier for you. So let me just open this figure histogram up and let me collapse this. And so here we are looking at all these. So we have item identifier and the count against it. So we have all these item identifiers, which are all categorical values. So think of these as SKUs or product names or whatever you want. But we have all these categories and we are able to see a distribution of how this is looking like. Looks like most of these item identifiers have sort of similar distribution, except over here with these two item identifiers. But that's fine because I feel like we might end up removing this from our analysis anyways because it doesn't seem to add too much value. Let's come to the item weight now. And item weight, we can see it's kind of distributed. Normally, we have some kind of a shape over here like this. So that's fine. We understand this now. Item fat content. We see there is low fat, regular, again a low fat, and LF and REG. So straight away we can see that there's some cleanup that we have to do at least within item fat content because low fat here, low fat here, and low fat here, they all mean the same thing, and regular mean the same thing as well. So we'll fix this. Item visibility is interesting. So we have sort of this kind of a distribution over here, and yeah, we'll see how we can fix this later on. And then we have the item types, and we have a few item types which are really high, like snack food and frozen food, and then some of them which are really low in the number of samples that we have within this data set as well. So that's kind of interesting to know. Item MRP. So it looks like we have different products which are in different price category range, and then we have different number of samples for that. So for example, for let's say this is dollars and $50 range, we have a lot of samples and then kind of drops, and then maybe at 99 or 149 or 199 we have peaks over here. That kind of makes sense. Then there is outlet identifier, which doesn't seem to give us much value. There is outlet establishment year. So these are the actual years. So we'll probably have to convert this into a usable format for our ML model. But nonetheless, it's good to know that when all these stores were opened, there is also outlet size. Looks like we have a good chunk of medium and small, and maybe a few of high outlet size or bigger outlet sizes. That's completely understandable. There is these outlet locations as well, tier 1, tier 2. It doesn't add much value, but nonetheless it's good to know when we are actually predicting at the store level. The outlet type, we have supermarket type 1, supermarket type 2, grocery, and type 3. Looks like we have a lot of data for supermarket type 1, so it's kind of skewed because we have a lot of data here and not much data for these stores, especially because we are predicting at each of these outlet type levels and not at the business level. So it's really important for us to have kind of uniform distribution, or maybe we might end up running each model separately for each of these stores, but then you won't be able to generalize this. Let's say we have another store that comes up over here. how are we going to make use of all this data for other stores that we had? So we won't be able to do that. So we probably have to build a generalized model for all these stores anyways. So those are the kind of things that we have to keep in mind. And then, of course, item outlet sales. Looks like we have outlet sales, which are, and this is again skewed towards the left as well. So that's fine. So we have an understanding of all the different variables that we have within our data set and how they are distributed within our data set as well. Now, if you wanted to do the same thing within Seaborn, where you want to just print this in your own console, so you should be able to run sns.count plot, which should give you something like this. So we are looking at the outlet size here, which is the medium, small, and the high, which we just looked at, and we get the count as well. And if you want, you can also print the histogram of this. So if you're looking at item weight, let's print this out, see what kind of weights do we have. So with this histogram plot, what all these tools are actually doing is they'll just create a bin for each of these range of values. So if it's ranging from 1 to 3, then it creates different sizes of bins and then puts them in each of these bins and do a count on that. So we should be able to get a histogram like this. So here we are looking at item weight. All right. So you can also run the same thing and also look at item MRP and also change the color. So you should be able to see something like this where you're plotting it against the number of counts we have. So that is just looking at a histogram distribution of how the data looks like, but we still haven't looked at how these variables relate to each other or how do they relate to the actual target value, like the output sales value variable. So we need to do all that correlation, collinearity, and other things as well. So let's keep moving on. And yeah, we don't have to worry about that. We'll do this in at a later stage as well, where we are just bringing in additional variables. So we'll do this later on in feature engineering. Next, we'll come to univariate numerical analysis. So univariate analysis is a type of analysis that focuses on understanding the characteristics of a single variable in a data set. So as you will see in this plot that we're going to build, it does give a bit more information on the kind of data that we're looking at. So again, the code very similar to what we just saw for histogram. So we'll create a figure which is just a subplot with the number of rows that we want. And here we are just looking at the numerical column. So if I just run this section, actually have to run all of these lines as well. Now, if I run this section over here, let's find out all the columns. So we'll be working with only 4 different columns: item weight, visibility, MRP, and outlet established here. So if I get the shape, so we're just working with 4 columns. So we'll have 4 rows in this figure univariate. That's fine. And then we loop through all of these. So if I look at all the columns, so we get all these columns now. And we'll just loop through this, add a trace, update the x-axis, y-axis, similar to what we did above. And we'll store that in a figure called figureunivariate.html file. Now let me run all of this and a file should be saved. Let me open that up. So here we are looking at the univariate analysis. So we're just looking at one variable against a dependent variable or the column that we're trying to predict, which is output sales. So we see item weight and output sales. So if we look at a scatter plot like this, the prices are all over and we're not able to, the way item weights are all over and there's no clear pattern that we can understand from this. So it's still fine. And then if I go into item visibility, so it looks like there's a lot of density for zero value and sales over here. So it doesn't add much value. But item MRP, so this is definitely interesting. Looks like there's some sort of banding happening on all these sections over here. So I'm interested to understand why all these values are empty and maybe if you want to remove this or not. But again, you can understand if you're looking at one variable against the final predictor variable that you're working for, how all these are distributed, it gives you an understanding of where you can take this. So similar to what we just did with univariate numerical analysis, where we are just selecting the numerical columns and looking at a scatter plot, we can do a similar thing by looking at the categorical columns and by building a box plot on these categorical columns to see how they're distributed. So let's look at univariate categorical analysis. And here, similar to what we were still doing, so here we'll select all the object type columns instead of numerical columns. So if I just select all of this, we'll see that we have about 7 columns, and these are all the columns that we're working with. And let me just run this. And here, if we were to get all the column names, so this gives us a list of all the column names. And we are just going to loop through all of that, build a box plot, add that to the trace, update the X and Y axis values, and then save that into a file, which is, I guess, a pattern that we've been following. So let me run all of this. And if I open up the file that we just got, we have all these columns over here, and we have the analysis against the output sales variable. So we see the item identifier and the output sales. So there are too many categories over here anyway, so we might end up ditching this column, but it's good to know that there is analysis that can be done here. And this is what I mean by traditional box plots. So you can see here item fat content against the sales column, and we see that we have this low fat, which is, we should have actually merged all this, but then we'll do that in the data cleanup stage. So we'll see how they're distributed within the each category, and we're able to compare that against all of them. So this is like looking at a histogram, but then it's also giving us a histogram for each of the categories, if you will. So we have the midpoint, we have the high value, low value, the quartiles, and so on. So from the item fat content, it looks like it's pretty steady, unless we should have added all this, then we could have seen a pattern, but that's fine. So if we were to look at the item type, which are kind of unique, we see that seafood has a good range of sales from minimum to maximum. It doesn't give much information, but looks like all the sales for all these categories are kind of steady. That's good enough for us. Then there is the outlet identifier, and not much information or outliers that we can identify here either. Next, if I look at the output location type, we have a very similar pattern, not much difference, or no, nothing really obvious stands out by looking all these plots. They're kind of in the range, and they're kind of uniform across all the categories as well. Except over here where we have the outlet type, supermarket type 1 and type 2. Of course, type 2 has a kind of lower box size compared to the supermarket type 1, where we have higher sales coming in at the supermarket type 1. So that's something to keep in mind. Next, we'll move on to bivariate analysis. And bivariate analysis is, again, another statistical analysis that involves investigation of two variables simultaneously, right? So with univariate, we were just looking at one variable against the sales. Now in bivariate, we look at clubbing two variables together and then looking that against the sales data. So we're looking at two variables simultaneously to determine empirical relationships between them. Now here we are using a tool called combinations, which will automatically give us like permutation combination of all these different types of variables. So let me just bring that in. Now I'll also run this column pairs. So what this is actually doing is, if I just look at column pairs, you see that we have all these categorical columns which are kind of clubbed against each other and kind of done like a permutation combination, which would have been a lot of work if we had to do it manually. But thankfully, we have this package which does it for us. Now, again, we are making a subplot over here, and we are making this bivariate analysis, and we'll give it the length of the column pairs, so which is about 21 columns or 21 rows that we'll have in the subplot. That's quite a lot. In real world, maybe by this time you would have eliminated some of these columns anyways, but we'll still go ahead, and it's good to have all this in one place to our analysis. And then here it's very similar. We are running a box plot again, but then we are running it against a paired plot, which is coming from here, where we are taking data from both column 1, so x of column 1, and then x of column 2, and then clubbing that into an x variable and then the y variable. So this will all make sense once we actually look at this box plot HTML that gets generated. So let me just run this block of code. So if I open this file up, there's obviously a lot of things happening over here. So you can see there's item identifier and item fat content and all these combinations that we can look through. But let me just go through this and see if there's anything obvious that stands out. Just look, this looks like it's just a lot of noise. We probably did not want all that in our analysis, but let's keep moving. So here we start to see some pattern where we have some high sales over here and here as well. So these are like low fat, but then the actual distribution comes in when we have item fat content as regular, and the dairy has a good amount of sales over here. So that's good to know. If we were to look at the low sales, so we have low fat content and breakfast items, so they have pretty less sales over here. And if we look at this, item fat content low, and then the type is hard drinks. So again, they are quite low in sales as well. This seems interesting over here, low fat and then hard drinks again on this section over here. But yeah, you can see, you can play around to try to understand your data really, really deeply, because we are understanding not just one variable, but we are clubbing item fat content and item type in this, and then looking at this. So similarly, if I scroll down, there is item fat content and item type. So actually the outlet identifier, so we can see by outlet identifier what kind of fat content got sold in those outlets. Not much information from that. Let's see this. So this is looking at item fat content and outlet size, and this is looking at again item fat content and outlet location. Nothing obvious over here except let's see this one. So low fat and tier 2 location has obviously less sales compared to low fat and tier 1 location. That kind of just validates our assumptions there, so that's fine. This is looking at fat content and supermarket type. So this makes sense. Supermarket type 1 has a lot of sales. If I compare that to supermarket type 2, so that's understandable. Now here we start to look at the item type against the outlet. Looks like this outlet is interesting over here. Seafood and outlet 6046 is interesting. But again, I'm not going to spend too much time on all this, because you would probably spend a lot of time just trying to analyze how all these are interacting against each other. Let me just scroll through quickly. So this is outlet identifier and the size of outlets and so on. So you can see there's a lot of data that you can go through in this bivariate analysis. So far we've seen histogram, we've saw the distribution, we've saw the univariate analysis, bivariate analysis, and they're kind of okay distributed. But what we really want to next look at is collinearity, or how these variables are dependent on each other. Because we are doing a regression problem, we don't want any dependence between these variables at all. That's why these are called as independent variables. And if there are any dependence between these variables, then we have to work on doing some feature engineering so that we essentially take that dependency out. Because if you think about the actual formula and other things, which I'll have in all these mirror boards so far, so you should be able to go in here and look at all these formulas for regression and other places where we also walk through this assumptions that we're talking about. So I'm not going to spend too much time on that in here, but I'll probably have a separate video in that section, or you can look through the previous projects to understand this a bit deeper. But essentially, when we do get to a regression model, we want each of these independent variables to have an interesting coefficient, so that we are able to understand how much each of these independent variables actually affect the output sales. And if we have two variables which are very, very dependent on each other, let's say we have a data set with BMI, body mass index, and the weight of a person, and these two variables are very, very correlated. So we can't really use that, because if one increases, the other obviously increases, and if one decreases, the other decreases as well. So in our analysis over here, we're just trying to find what are these columns which are very, very common and which move together in a pattern, so that we can remove that or feature engineer it. So that is what we're doing with collinearity. And there are a few types of there are a few ways that we can do this as well, which we'll see, because we are working with both numerical and categorical values. So the most straightforward way to look at this correlation is by looking at Pearson correlation, like what we have. And we can easily do that by calling this function .corr. So let me just initialize this plotly express, which has a heat map function, and let me just run this and save this in here. So now we should have a file called correlation. So if you were to look at this, so we have item weight against item weight in this over here. So that is why we see a good positive correlation of 1 over here. But what we're really interested in is all these boxes over here where we are looking at item visibility against item weight. So it doesn't look like there's any correlation over here or any of these. So that is good. But then we'll keep continue on because this is only numerical types. We can also display the correlation as well. So if I look at this and let me just print this out. So you should be able to see this sort of a matrix, but then it's really difficult to read this. So we can do a heat map plot within Plotly. And if I save this, so this becomes Pearson correlation. So now if I open this up, you see a matrix, but then it's also color coded. So here, if I hover my mouse over this, you should be able to see what kind of correlation each of these boxes have. Looks like there's not much correlation at all. So again, if you were to revisit a few of the previous videos, you'll understand that if the correlation is +1 or -1, then that's a strong positive or negative, which is what we're looking for in here. So if it's around 0, like what we've seen here, 0.07, that doesn't add much value at all because it just says it's in between. There's no correlation there. Now, instead of doing all this with Plotly Express, you can also get the same thing with Seaborn as well. So if I run this, so you should be able to see a heat map like this, but then it also prints out the value for you within your terminal. So you can see here, these are all like 0.00, so they're very much close to 0 on all this. We're not worried too much about all these diagonal values because they're of course the same variables on X and Y axis, right? So item weight against item weight, item visibility, item visibility over here. So we're interested in all this and doesn't look like there's much correlation there. So next we can move on to looking at categorical feature correlation, because what we saw here are only Pearson correlation for numerical columns. We also want to understand how these categorical columns are correlated. And for that, we use few techniques like chi-squared, Kramer's V, and other things as well. Chi-squared, I've covered it in the previous project where we went in depth and understood how this works. But it's good that we were able to code this in the previous project, but then we are still reusing it today in this project, and we'll probably use that in the future videos as well, where we want to look at correlation with categorical values. So as a simple example or a simple explanation of this is chi-squared is a test of independence and checks whether there's a relationship between the two categorical features, which is what we really want. And within chi-squared, there are the concepts of null hypothesis and rejecting or accepting this and getting to a statistical significance. But essentially what we're looking at is a p-value which is less than 0.05, which gives us 95% confidence that this did not just occur because of a random event or a random choice. This is a statistically significant event, so we have to pay attention to the p-value, right? So that is what statistical significance is. And here we are looking at categorical values. So if we start by looking at all this, so we have all the object types, all right? So we have 7 or 8, was it? We have 7 columns, which are all categoricals. And we'll do the same thing where we build a combination or column pairs. And if I just show you what we have here, so this just builds a combination of all these variables or permutations against them. So for this, let's reinitialize a results array and we'll start putting all of them into the results list. So if I were to just talk through this, so we are looping over these column pairs. So imagine we had this example over here, item type and outlet type. So those would be column 1 and column 2. We built something called as a cross tab. So if I hover my mouse over it, you should be able to see the documentation on this. So it computes a single cross tabulation of 2 or more factors. So we're providing that. And then this is fed into this chi-squared function coming from stats library. And we pass in all those values and we get values like chi-squared, p-value, degrees of freedom, and all these values. And we just append all that into the results list. And finally, we convert all this into a pandas data frame and then look at all these values which are less than 0.05, right? So hopefully that made sense. Let me just run this. So when we just print out all the combinations which had a p-value less than 0.05, which in our case means that there is kind of correlation between them. Then it's then we see these values over here, where we have you see this minus e to the power of 120, minus 123, and minus 144. These are like really statistically significant, but so are these. But then these kind of stand out, these two values. And if we analyze this, this is looking at identifier and the fat content, and here we have the fat content and item type. So it looks like these two columns are very, very correlated, and these two are as well. So in our final data set, maybe we want to remove the item fat content, because if you think about it, the fat content and the item type, they're kind of similar variables. So if you're looking at chips or biscuits, then they'll have steady fat content. So they're kind of correlated, right? So maybe we can remove one of these columns to make our analysis a bit more efficient. So that's one thing that we can learn from this, and then we will do some feature engineering in the future and see how we can deal with this. But yeah, so these are the exact kind of things that you want to pick out at this stage when you're doing exploratory data analysis. So one thing to keep in mind when we're doing this chi-squared is we get a p-value like this, which gives us statistical significance, but then it's really difficult to interpret this with the context of what we're looking at. So that is where we have the Kramer's v-test as well. And one other thing was, if you're thinking about item fat content, which is row and regular, that's fine. But then item type, so there can be different item types as well. So here we have a problem with chi-squared, where the value of chi-squared statistic itself can increase with the sample size or the number of categories. So within item type, we had a lot of categories, then the chi-squared statistic can increase. And that kind of defeats the purpose for us, where we are looking at the correlation between these two. And that's where Kramer's v-test comes in, and it provides a normalized measure of association between these two variables, and which is exactly what we want to understand. And it also deals with these problems of sample size, the number of categories, and so on. So think of Kramer's v as a version that was built on top of chi-squared to make it a bit better. So we'll use this Kramer's v and see what kind of results we get here. And for this, we are going to do some pre-processing, label encoder. So we are going to pass in outlet type and all these different types, and then encode it so that they have their own separate columns. So you'll see what I mean by that. Let me just run this. Label encoder is not the only encoder. There are other data type encoders as well, like one hot encoding and other things. But we'll use that label encoder here. So if I hold my mouse over it, you can see this transformer should be used to encode target values, and then it encodes between 0 and n classes minus 1. So if we had a category called good, better, best, then that would be 0, 1, and 2. So that would be the kind of label encoder. So I can run all this. I'm just making a copy of the data frame, creating empty data frame called data encoded over here. So if I look in here, it's there's 0 rows and 0 columns, and we loop through this. So if I show you what columns we're working with, so these are the columns, and we loop through this, and then add to the data encoded column the label, which is the label encoder, and we fit a transform and then add it here. So if I just run this and show you what we get with data encoded. So you see here with outlet type, we converted the outlet type to just zeros, ones, twos, and so on. So we have outlet location 0, 1, 2 and 0, 1, 2 on the outlet size as well. So that kind of that's good for us because we want to work with numerical values now for these Kramer tests. So here so we have a double loop. We loop within a loop over here, where we first take, for example, if we worked with outlet type as variable 1 over here, we loop through, work with outlet type, and then when it comes to the second pass, it looks at outlet size within this section over here, and then looks at outlet location within this pass. So we're doing very similar to what we did in the past, where we are still calculating the chi-squared metrics using the stats model. So if I scroll up, you should still see the same line that we're using. But then we do a few additional calculations over here, where the Kramer's v is coming in here, which is the chi-squared divided by the observation times variable 3. Variable 3 is this value over here. Again, for the formulas and exactly how all this works, there should be a mirror board which should be coming up soon with all these explanations and a separate video as well. But let's just work through this. So we are calculating Kramer's V and then appending that into the results list over here. And then finally, we'll create a data frame out of this to understand how this data looks like. So let me just run through this all again. So that's good. And I'll also run through this. And if I look at the results CV, so we have some values over here where we are looking at outlet type, size, and location against themselves. So if we look at all these, so this is good. So it looks like there is 0.42 correlation between outlet location type and the outlet size. So that kind of makes sense. The location, if it's a big location, then the size of the outlet can increase, but not all the time. So this is something to pay attention to. It's not really major because it's not really close to one. If it was close to one, then we probably need to remove one of these. But in this case as well, maybe we can, yeah, remove outlet location type or outlet size completely, and see how that affects our model as well. So again, this we would have completely missed if we hadn't gone through this correlation exercise. Now we looked at correlation for just the numerical types with Pearson, with just the categorical values with chi squared and Kramer's V, but we also want to look at correlation between numerical and categorical columns, and that is exactly what we're doing here. And for that, we use one-way ANOVA test. So ANOVA test is, again, there'll be a separate video or a Miro board attached to this to understand this better. But it tests for statistical difference among means of three or more independent and unrelated groups. And like I said, this is used when there's one categorical independent variable and continuous dependent variables. And so this is good for when we are looking at both numerical and categorical features for correlation. Again, running the code on this is very straightforward. So we are again after the p-values to get the statistical significance, and here I guess the key function is over here, which is coming from stats, and it's f underscore one way, which is the ANOVA test, and then we append the results. So let's walk through this. So here we are looking at this product. So in the past, we were looking at the combination import from iter tools package, but now we are looking at the product. So here we have the numerical columns and categorical columns. So if I just show you this, so we have all the numerical columns and all the categorical columns, and we want to build a pair by looking at the product of each. So if I run this and look at the column pairs, now we have item visibility against our outlet type. So we have all these MRP, which are all the numerical columns. The establishment year was a numerical column, and so on. So we are looking at all these item weight against all the categorical columns, which are on this side over here. So we loop through over this, and we call the first one the numerical column and the second one the categorical column, which is what we have here, numerical and categorical. And we loop through this and we look at the categorical values, and we build a filtered list off of this to get the ANOVA test, get the f-stat and the p-value, append all that, and finally look at the result. So let me just run all of this. So all these values are actually values where the p-value is less than 0.05, or it is statistically significant, or they're really, really correlated. But one thing that stands out here is this, which is output establishment year and the output location type. So it looks like these two are really correlated. We might have to feature engineer this, or work on a feature which can be used in our data set in here. So there is also item type and item type, which has a really good correlation again. So maybe we want to take out item type because we saw it was also having a good correlation with other columns in the previous test as well. So far we've looked at only these variables against each other to figure out collinearity, because in here, at least in regression, we really don't want them to be correlated. We want them to be independent of each other. So that is what we are going for. And if they're dependent, then we try to remove it or do some feature engineering on it so that it can be used. Now, the next step is actually looking at if these variables or these features that we're using are actually correlated with the target variable, which is the output sales in our case. Because if we pick an independent variable and that has no correlation with the output sales, then that is of no use for us in using in regression, because that won't give any information, or it won't have any impact on the output sales at all. So in the next section, what we want to really look at is correlation of numerical types or categorical types in the next section against the target in our case, which is the output sales. So if we don't see any correlation here, then we probably don't want to use that feature, right? So let's go through this exercise and then see what kind of correlations we have. So here is where we are looking at a bar plot for all the features against the target. And if you remember, the target was actually the item outlet sales. So we are plotting this bar chart against this to figure out the correlation, and then we'll save that in a file called figure correlation with respect to target. So we are expecting a bar chart with correlation values. So let me just run this section now. And if I open up my correlation, so this is what we have. So it looks like item MRP and output sales are correlated. So that's good for us. So items MRP or retail price is able to predict how much sales we would have. So that kind of makes sense. Item visibility has a negative correlation. So the less items that are visible, the less sales we have. That kind of is good as well. Item weight, I don't see much dependence on the sales. So do we really want to use this, or in your problem that you encounter in your data science world, do you really want to use a variable that does not have enough correlation with the output variable that you're trying to predict? That's something to decide. And of course, output establishment here, this doesn't have much impact on the sales either. So we probably want to get rid of item weight or the outlet establishment year. So this is kind of good to understand which are the features that are really driving the output sales, because when you get to explaining this to your team or the stakeholders, this will be really, really important. Next, we want to do the similar exercise for categorical variables against the target. So here we are running again the ANOVA test, and then we are doing this for both the numerical columns and categorical columns. And all these functions, like I said, keep a repository of this so that it can be used again and again in future projects of yours. But let's just run through this. So we create numerical columns, categorical columns, and a pair of this using the products. So if I run all this, so you should be able to see what kind of column pairs we are working with. So we have the MRP, the establishment year, which are all the numerical columns. And here are all the categorical columns that we have. And we were able to build a product or a permutation combination sort of a thing over here using this function. And we loop through all of this over here, build categorical values, and create a filtered list like this, which goes into a ANOVA test. And we append all that in the results. And finally, we build a results data frame and look at all the columns which have a p-value less than 0.05. So when we look at the actual results, so we are looking at p-value less than 0.05, which says it is statistically significant. Now, when we look at this, so we see that we have like outlet size or outlet location, which has a significant amount of correlation with the output sales, which kind of makes sense. So if the outlet is a bigger size or a bigger location, then we obviously get more sales. So probably these are the categorical values that we really need to keep within our analysis. I do see this E minus 251 item identifier, which is having a good indicator on sales, but then we also saw that it has a lot of values. So there are various types of values with an identifier, which doesn't add much value. So probably we might get rid of this and hold on to all these values. Next actually comes the feature engineering. So far what we've done is just looked at how the data looks like, what can the data tell us by doing exploratory data analysis. Now all the learnings from that data analysis, we can use that in feature engineering, like what columns to drop or what columns to fill with some data so that all the null values can be cleared up. So these kind of things we do in feature engineering and really set ourselves up for success when we do get to the regression part. So here we are doing an item weight because item weight had some null values. When we do encounter a null value, we just fill that up with the max value like here. And that would be our item weight. And outlet size as well had some null values, which we'll just fill it with small. And for item fat content, we saw that there was low fat, LF, regular, and regular as well. So we'll clean all that up and then have a standard low fat and regular. And also for output establishment year, instead of having it as a year, we'll actually create a new feature called outlet age, and we'll subtract the year with the output year and establishment year and have that outlet age. And finally, we can just drop that output establishment year completely. So let me run all of this. And once this is run, you should be able to see there is a new data frame called DF. And if I open this up, so we have all these now. So you see there's only two types in item fat content, whereas in DF train. Whereas if I go back and look at my other data frames, so you see there are also other values which contribute to 6.4%. So within DF, we have only two values, so that is good. And we also fixed a few of the columns, so they are all good as well. Next, we will encode the categorical variables. So you see here, we have all these categorical variables, but they are not really understandable by the machine learning model. So we need to convert this into numbers or numerical values so that our models can use it. So these are all the columns that we want to encode. So let me just run this, and we will do the label encoder again and then fit transform and then load all these columns. So once all these columns are encoded, we can run these few lines and look at how our new data frame looks like. So we are also dropping this item identifier like we saw in the past. It has a lot of categorical values, but then it doesn't add much value at all. And here is the function which is also doing a bit of encoding, which is called as get dummies. And if I hover my mouse over it, you'll see it converts the categorical variables into dummy indicator variables and creates separate columns out of this. So if I look at DF new data frame now, so you'll see only zeros and ones and numerical values. But then if I keep scrolling, you'll see that there are a few more columns than we initially created. So we have for each of the item types, we have a separate column. Like we have item type breads, breakfast, canned, which are all just Boolean values, like we see here. And this can be used in the models that we are going to build. So this is a good step in feature engineering for us. So next we look at splitting the training and testing data, which is coming from this function over here from sklearn. Let's bring this in, and we'll assign all the columns, which are all the independent variables, into a data frame called X, and then the output variable, which is what we're trying to predict, into Y. So if I just run this, so now we should have two different variables, and we should be able to create train and test data on this. Now, instead of creating a train test split here, what you could also do is do this, but then also bring in the test CSV that is in this Kaggle competition as well. So if you have this, you can use this as an evaluation data set or a test data set. So either way is fine. But for now, we can just work through this train CSV and create a split ourselves where 80% is in the training set and the test size is 20%, which is coming into the test set over here. So let's just run this. So now if I look at the training set, so if I look at X train, we have around 6,800 rows, and X test we'll have around 1,700 rows, which is 20%. So that is good. Next, we'll work on building some models on this. So we'll go through about 10 different models that we can build, and we'll compare each one of them and understand how each one of them work as well, but not in too much depth because we'll probably have separate videos on that. Here, the goal is to just go through the code and understand each one of them. But yeah, I do encourage you to go in and look at the Miro board or the other videos to try to get an intuition of how all these models are working. So first, we'll build regular linear regression models. Like here, we have linear regression. There's also elastic net, random forest, some MLP regressors, which is neural net, gradient boosting, which is ensemble learning, and so on. So we'll go through each one of them and see what we get. So we have linear regression. I've tried to put in some information on here so that it's easy for you to read and understand. So linear regression is what we've all seen in the past. Elastic net is again a parametric regression, but then it combines L1 and N2 regularization. And this is really interesting because we really don't want overfit our models and we want a generalized model, and these are really beneficials. So I encourage you to go in and look at this videos related to this as well. Next, we have random forest regressor, which is looking at random forest. Then there's gradient boosting, which is ensemble learning, and there are separate mirror boards for all this, which we've covered in the past for at least ensemble learning, where you'll see bagging, boosting, and so on. Next, we have MLP regressor, which is a multi-layer perceptron, a neural network which consists of input, hidden, and output layers. And this is really good for modeling non-linear relationships. So we'll bring in all of these into a list called models, right? I have to add all this. So let me just run all this first. So we bring in all these functions from all the libraries, and we should be able to run this line, which is all the models now. And we'll initialize course names and cross polls. And what we're doing here is basically looping through all these models and then running a cross val score where we give it the train and the test data set and the number of cross polls, which is three. And then and then what this does is builds the model and then it prints out the values and will store all of them in scores and the names. So if I hover my mouse over this cross val score, so this is coming from sklearn, and this initially takes in the model, which is J over here in our loop, and then we give it the train and the test data and the cross folds as well, which we are saying three, and then we'll append all these scores and names into these lists and print them out. So let's run this and see what kind of results we get. So it looks like we have some values over here. So you see for linear regression, it's about 0.49, and here we are looking at the scores, which are the R squared metrics. So this helps us validate or compare models against each other. So the best model looks like is GBM, gradient boosting method, and also RF, which is random forest regression, which is fine. But again, these are all within zero point 0.5 to zero point 0.6. So it looks like this model is only able to go up to that. Again, I encourage you to go back and do a bit more feature engineering and see what sort of results we can get by removing a few columns or doing a bit more feature engineering, see if we are able to push this above zero point 0.6. There are also voting regressors. So we've looked at all these one, two, three, four, five, six different types of models. And next, we'll also look at voting regressor, where it's an ensemble meta estimator that fits several base regressors, each on the whole dataset. Then it averages the individual predictions as well. Not used that much, but then if you have a linear regressor, gradient boosting, and a neural network, and you want to build a voting regressor on top of it, where you get all this on the whole data set, but then you want to average out and then get the final predictions, you can use this voting regressor technique. And here again, like we showed, so we are using linear regression, GBM, ML, P, and you can give it as many as you want and then build a voting regressor. So let's see what kind of results we get on this. So we've got some results from our voting regressor over here. So we see for linear regression, it was R2 value was this, and GBM and MLP. And from the voting regressor, we get an average, which is 0.55, which is actually not bad, but it's still worse than what we had over here for GBM on its own. Next, we'll look at stacking regressor, where it consists of stacking the output of individual estimator and use of a regressor to compute the final prediction. And it kind of allows us to use the strength of each individual estimator by using their output as input to the final estimator. So this is kind of good. So let's see what results we get from this. And here we are feeding in a linear regression and a GPM. And we'll put that into a stacking regressor, which is coming from sklearn ensemble. And we'll see what we get with the cross-val score here. So it looks like with stacking regressor, we have better results. So we are around 0.59. Still haven't gone over zero point 0.6. So this is still something we have to hit, but this is still good, 0.59. And we use the stacking regressor. And to get the final R2 out of this regressor model, we can do an R score print, and it's still zero point 0.5. 9. Next, we have the ninth model, which is generative additive models. Again, for all these models that we're looking at, there's usually a mirror board that I've already worked through in the previous video, or I'll attach to this in the course section so that you can go in and watch that video and understand all these models. Because just running these models is not enough. Getting an intuition of how these models are working under the hood is what will be really useful when you encounter a business problem that you really want to use these models in. And similar case with generative additive models as well, GAMs. So GAMs are really useful when you are building a model that you want to track the non-linear relationships. So unlike linear models that assume a straight line relationship between variables, GAM uses a smooth function such as splines and so on to model complex behavior between variables. So if you have a distribution where you want to have a regression like line like this, a smooth curve which is non-linear, then GAMs would be really good. Because we'll probably go through this in the theoretical section, but you can work through each of these in sections and then create splines and so on. But nonetheless, we will bring in all these from a package called pygam, and then we should be able to run all the similar kind of things, but then usually go through the R2 score here and here. So there are linear GAMs, Poisson GAMs, and gamma GAMs, and etc. So let's just run this on gamma GAM and see what result we get. Looks like gamma GAM went over zero point 0.6, so that is good. Let's see what we get for Poisson GAM. So while this Poisson GAM is actually running, let's just move on to the gradient boosting method. And here we have some code which we've already looked at for when we did the voting regressor and so on. But nonetheless, we can run this on its own to get some predictions as well. And that's how you run this. So there is a gradient boosting regressor which is coming in from sklearn ensemble. And we just pass in the X train, Y train, and finally pass in the predictions to calculate the R2 score. So from all these models that I've run so far, it's only been 0.59 to zero point 0.6. So I wanted to try extreme gradient boosting as well. Now, extreme gradient boosting has all these benefits of scaling, regularization, missing data handling, and so on. And it works. It's actually an ensemble of trees, which is an extension of gradient boosting regressor. So XGBoost has all these benefits. And I've also gone in depth in the previous section where we also looked at how all these the formulas and other things work for XGBoost as well when we looked at insurance pricing problem. So I encourage you to go and look at that as well. And the code from that we are using it here, so we can bring in all these packages. And first we are looking at RFE, which is feature engineering. So first we look at RFE, which is recursive feature elimination, and we only keep the features that are useful for us. So it kind of does the job that we were trying to do in the exploratory data analysis part. So we can bring that here. XGB regressor is what we are getting from a package called XGB Boost. And here we are kind of building a pipeline similar to like voting regressor or stacking regressor that we were looking at. But then here we feed one output to the others and we are building a pipeline here. So initially we do the recursive feature elimination, and the output of that we'll feed that into XGB, and this would become our pipeline. And pipeline is coming from package sklearn as well. So let me just run all of this. Next, we want to do some hyperparameter tuning, and we don't want to do all this manually. So for that, we will be using search base CV, and this is coming from a package called scikit-learn optimize, and this helps with doing hyperparameter tuning. So we give it values like integer values, low and high, and then it just goes through the algorithm goes through all this, tries to find the best hyperparameters for us. So we'll run this now, and when we do come to the base search CV, which would be the model, we give it the pipeline that we had, and also the search spaces, which is over here, all the hyperparameters, and we give it the number of iterations, the jobs, and other things as well. So this becomes our model, so we can run this. And finally, when the model is ready, we can do a fit on that and get the values out of it. And this usually takes a while. So if I just run this, so you'll see it starts iterating and it goes through the various iterations to come to the value. And what I've seen here is, within this problem at least, XGBoost was able to get a value over 0.66162. So it is very similar to the other models as well, but then this was able to push it a bit more. And you can see here it's already starting to go through all the iterations. So I'm not going to wait through for this to finish, but I encourage you to go in and play around with this and see what kind of results you get. But again, once we do this, this is not the end of it. In more of the projects, we'll also be looking at creating an API and hosting this and using this in real world. But I would also encourage you to build this model out yourself and also do some feature engineering, see what features can be eliminated to get better, and also make this into a separate farm module so that you can reuse these functions again and again, like the exploratory data analysis that we did.